Hello everyone, welcome to the YouTube channel. This is Stelzer Science, and this kicks off the first physics YouTube video that I'm going to do this year. So for those of you who haven't watched any of my videos before, I really like to use this YouTube channel to actually work on the review. And I like to do the review, and I try my best to kind of talk what I'm thinking out loud. That way you kind of can see my thought process as I'm doing these questions. So we're going to do the exam 1 review today. We're going to split it up into 2 sections. I'm going to do the multiple choice in one video, and I'm going to do the FRQs in another video. This video is going to be for the multiple choice. So let's go over to the multiple choice questions. And one more thing before I get started. I 100% forgot the answer key at school, so I don't have the answer key in front of me. Let's hope I don't get anything wrong, but I was too lazy to actually look up the answers for everything. So if I get something wrong, yeah, it's not going to happen. All right. Surely I can't make a mistake. I never do in lecture. All right, let's go ahead and get started. Let me pick a color here. I'm thinking red today. I got it. All right. And I want to get rid of this again. Full screen. All right. Multiple choice, 1 through 10. Let's get going. An object sliding to the right along a straight line on a horizontal surface. The graph shows the object's velocity as a function of time. What is the object's displacement during the time depicted in the graph? So we're trying to get the displacement of the object. This is a graph of velocity versus time. Displacement from the velocity versus time graph is the area under the curve. And I can see that the area above the zero equals the area below the zero. So I know the displacement here is 0. We went the exact same amount of time going in the forward direction as we did in the reverse direction. Almost knocked down my lamp. So the total displacement is 0. 2, a ball is thrown with an initial speed of 20 meters per second at an angle of 60 degrees to the ground. If air resistance is negligible, what is the ball's speed at the instant it reaches its maximum height from the ground? So when I do physics problems, I love to make just simple figures to show me what's happening. I really think it's important to visualize the problems correctly. And for me, that involves drawing. So what do we have? We have a ball. It's being launched 20 meters per second at an angle of 60 degrees. And it's going to make an arc because this is going to be in projectile motion. And we're trying to find what's the speed right when it reaches the apex of its flight. We know that at the apex, the y component is equal to 0, which means any speed that this ball has at the maximum height is only due to the horizontal component. Last connection, there is no acceleration in the horizontal direction, so the starting horizontal velocity equals the ending horizontal velocity, or I guess the horizontal velocity at the apex. That velocity, Vx, is equal to 20 times cosine of 60, the cosine component of the vector. And if we do that, 20 times cosine of 60, it's 10. Again, I don't have the answers. I am just doing this on my calculator right here. It's also low battery, so it's plugged in. An object is thrown with an initial speed v near the surface of the Earth. Assume that air resistance is negligible and the gravitational field is constant. If an object is thrown horizontally, the direction and magnitude of its acceleration while in the air is downward and constant. The acceleration for any object in projectile motion is always downward and constant, and specifically it's negative 9.81 meters per second squared because it's gravity. That's what gravity is. This term, gravitational field, is a term that physics is using more and more often. The gravitational field just refers to that near the surface of the Earth, there's always, no matter where you are, you're in an area where the acceleration is down. That's it. All right, 2 students want to determine the speed at which a ball is released when thrown vertically upward into the air. One student throws the ball into the air while the other student measures the total time that the ball is in the air. The students use a meter stick to measure the release height of the ball. Which of the following equations should the students use to determine the speed at which the ball was released? Okay, so let me just reread it. Okay, we need to pick a kinematic equation of motion that these students are going to use. So the answer is going to be one of the first two. We're not going to use this kinematic equation of motion. It does have initial launch velocity. That's what we're trying to find. We're trying to find what was the initial velocity. But notice we're taking time. We're getting data for time. So let's pick an equation where we can plug in time to get our answer. We are also not measuring the height of the ball. We're measuring it's stated that we're only measuring the release height of the ball. We're not measuring how long it takes or how far it goes up. We're only measuring the release height and anything to do with time. Which means the answer here is going to be B. A is not going to work because we're not measuring the time. We're not measuring when the ball reaches its highest point. We would need that displacement in the y direction too if we're going to stop the timing there. This is like your catapult experiment. You probably stopped time when the ball hit the ground again, not when the ball reached the apex. So the answer is B. An automobile traveling on a straight level road has an initial speed v when the brakes are applied. In coming to rest with a constant acceleration, it travels a distance x. How far will the automobile travel coming to rest if it had the same acceleration but initial speed of 2v? The answer here is 4x. And your intuition probably wants to say 2x, but we're moving twice as fast, so that means we're going to go twice as far. But you're not accounting for the fact that we have acceleration here. So we're going to use this equation, v final squared equals v initial squared plus 2a delta x. We're coming to a rest, which means v final is 0 equals v initial squared plus 2a delta x. So we can say that 2a delta x is equal to v naught squared, because we can also say that a is negative. So what that means is if we, let me move this down a little, is if we double the velocity, this velocity is squared, which means we are going to quadruple the displacement. So because there's acceleration there, it's going to be a 4 times amount, not a 2 times amount. If there is no acceleration there, then it would be 2 times, but there is acceleration. And things behave differently when there's acceleration. A duck flies past a truck that is at rest. The duck takes 2.1 seconds to fly at constant speed vd from the back of the truck to the front. Later, the truck travels along a flat, straight roadway with a constant speed of 3/4 vd. The duck flies past the truck again with a constant speed of vd, flying in the same direction that the truck is moving. How long does it take the duck to fly from the back of the truck to the front in this case? Okay, so essentially we have this truck, that was a bad straight line, and it's moving 3/4 vd, and the duck is moving vd. So the duck is moving faster than the truck. If the duck takes 2.1 seconds to fly across the truck regularly, how long will it take to fly across the truck when the truck is moving 75% of its speed? So essentially, the relative speed of the duck moving across the truck now is vd minus 3/4 vd, which is just 1/4 vd. The duck, compared with respect to the truck, now has 1/4 of the velocity it had previously, which means it's going to take 4 times as long. 2.1 seconds times 4 is 8.4 seconds. Again, relative velocity gets a little bit confusing if you're not careful with what you're defining with respect to. But let me put this another way. When the duck flew across the truck not moving, it took 2.1 seconds. Now that the truck is moving as well, the duck is going to take longer to get past the truck because the truck is also moving forward along with the duck. So the question is how much longer? So it's already not A or B. Because the truck is moving 75% the speed of the duck now, the duck needs to be, the duck is going to take just that much longer to go across because it's moving with 1/4 of a relative velocity. It was kind of a scuffed explanation, but the answer there is D. Okay, let me zoom out for this one. The graph above represents the position x, the velocity v, and the acceleration a as a function of time for a marble moving in one dimension. Which of the following could describe the motion of the marble? Rolling along the floor, then bouncing off a wall, rolling down one side of a bowl, then rolling up the other side, rolling up a ramp, and then rolling back down, falling, and then bouncing elastically off a hard floor. Okay, so we kind of have to decipher these graphs. There is acceleration, which means that velocity is changing. And what really speaks out to me here is notice how velocity reaches 0 at some point. That means at some point the marble's velocity has to be 0. Also notice it's pretty continuous. We don't see a big jump in position. So position goes down and up. It doesn't do something like, where it goes down and then it like jumps up, or does anything weird where it just goes down and then back up. Neither does velocity do that. It's a very continuous track. So because of that, rolling along the floor, then bouncing off a wall, I don't think it's A. A's velocity versus time graph would look more something like this. Rolling along the floor, and then as soon as it bounces off the wall, it has the same velocity going the other direction. Rolling down one side of a bowl and then rolling up the other side. I don't think it's B, because B doesn't have an instance where the velocity is 0. If it rolls down a bowl and then up on the other side, the velocity, speeds up and then slows down, but it doesn't reach 0 in the middle of that. It does something more like that. Rolling up a ramp and then rolling back down. So going up and down. I think that one could work. Falling and then bouncing elastically off a hard floor, and for the same reason that A wasn't true, D is not going to be true. The answer is C. And it's the only one that really has an instance of, okay, we have a velocity, and then it gradually slows down, it gets to 0, and then it speeds back up again. If we picture marble rolling up a ramp, draw a ramp, the marble is going to go quickly, and then it's going to slow down, and then it's going to stop, and then it's going to come back down and speed up. That's what's happening here. But what's weird is kind of the way they drew velocity. They're defining this way as the negative direction and this way as the positive direction. But we can change our directions if we need to. A student throws a rock horizontally from the edge of a cliff that is 20 meters high. The rock has an initial speed of 10 meters per second. If air resistance is negligible, the distance from the base of the cliff to where the rock hits the level ground below of the cliff is most nearly. Okay. We have a cliff. That cliff is 20 meters high, and we throw a rock horizontally 10 meters per second. That rock is going to fly down, and it's going to hit the ground, and we're asked for this distance. How far away does it land? So I think pictures are really helpful. that gives me a better idea of what to do here. So this is a projectile motion problem. The first thing I'm going to do in order to find this distance is I want to find how long it's going to be in the air for. So let's go to a kinematic equation of motion. Let's do the delta x equals v naught t plus 1/2 at squared. And specifically, we're going to analyze this in the y direction. So delta y, there is no initial velocity in the y direction. Everything is horizontal. Pretty sure it said that, right? Yeah, it throws a rock horizontally from the edge of a cliff. So delta y is equal to 1/2 gt squared, because acceleration is that of gravity. Let's just say 10 t squared, and then delta y is 20. You can say -20 and -10 too, but I'm going to call this way the positive direction so that I can keep everything positive. Okay, so 0.5 times 10 is 5. 20 divided by 5 is 4. It's the square root of 4 is 2. We're in the air for 2 seconds. Now we can look at this in the x direction. In the x direction, same equation. Delta x, which is what we're solving for, is equal to v naught t. The initial velocity in the x direction is 10 meters per second. And there is no acceleration in the x direction, so now that goes away, and it just looks like that. Delta x is the distance we're solving for, and the time we just found was 2 seconds. So the distance is 20 meters. Almost done here. 2 more questions to go. A cart is constrained to moving along a straight line. A varying net force along the direction of motion is exerted on the cart. The cart's velocity v as a function of time is shown in the graph above. The 5 labeled points divide the graph into 4 sections. So we have velocity. We're graphing velocity versus time here. Which of the following correctly ranks the magnitude of the average acceleration of the cart during the 4 sections of the graph? So we're trying to get acceleration from a velocity versus time graph. Acceleration is the slope. You really need to commit this to memory. To go from position to velocity to acceleration, it's the slope. To get acceleration, you take the slope of the velocity versus time graph. To go from acceleration to velocity to position, it's area under the curve. That's already shown up twice in these 10 questions we've done. So we're trying to get the slope, and also another thing, we're asked for the magnitude. What that means is we don't care if it's positive or negative, it's a positive or negative acceleration. We just care that there is acceleration. So 0 should be the lowest. And actually, before I look at everything in detail, the acceleration from B to C is 0. And since we're ranking magnitudes, that should be the lowest one. So we can already narrow it down by just crossing out which ones don't have the acceleration of A to B as the lowest. And actually, that's not right, that's not right, that's not right. Only D is correct here. When velocity is not changing, there is no acceleration, which means the acceleration from B to C is 0. So it's the lowest. We can verify everything else. So we're ranking the steepness of the slopes, in other words. So the steepest slope out of these sections is C to D. It goes down by 4 blocks over by 2. The second steepest looks like A to B. It goes up by 4 blocks over by 3. The third steepest is D to E. It goes down by 2 over by 3. And then BC is obviously last. So CD 1, AB 2, DE 3, BC last. Last questions, projectiles 1 and 2 are launched from level ground at the same time and follow the trajectories shown in the figure. Which one of the projectiles, if either, returns to the ground first, and why? Let me reread this one. So intuition wants to tell you number 1 here. Number 1 will take long, or which one hits the ground first. So intuition wants to tell you number 2 here. Number 2 is going to hit the ground first because it's moving less up to begin with, and how long something is in the air depends on the vertical velocity, not the horizontal velocity. It's all purely on the vertical velocity. However, we're missing some information. We don't know the relative speed these two were launched. So the answer, I believe, is D. We need to know if it specified that these two were launched at the same speed, then we can say that one will be in the air for longer, 2 will hit the ground first, since 1's speed is a bigger concentration of vertical velocity than 2. But we're not given that information. We need that information to understand, because if 1 can be launched upward at like 1 meter per second, and 2 can be launched sideways at 4 million meters per second, 2 is going to be in the air longer. So we need to know what the starting velocity, even though 1 has a better angle. So we do need to know that in order to get the answer. All right, that is it for the multiple choice. So just a reminder, on an AP exam, you get 2 minutes per multiple choice question. Timing wise, I don't know how long this video is at the moment, but work quick, and these questions are hard, so really, if you can see shortcuts, make shortcuts. Really rely on your conceptual understanding of what's going to happen for these ones. These are hard questions. If you have any questions on any of these, if I didn't explain something well, then ask me. Feel free to ask me in class, but otherwise I will end this video and then we will get started on the FRQs next. Alright, see ya.